This is a continuation of notes for section 4.3. So yesterday we were in this section and we covered all this, and I purposely left off this last little part. So I'd like you to open your notes to this page and we'll fill this in, and we're going to kind of be hopping around here. So if you need to pause the recording to find the right page, feel free to do that. So we talked about how the integral, the definite integral with certain limits, which we said we're going from a to b of a function, gives us the area under the curve. And loosely speaking, the f of x we would consider the height of rectangles, the dx we'd consider the base, and this kind of means loosely that we're adding them all up on the interval. Well, the area under a curve is considered negative when it's under the curve, and why would that make sense with this given definition? Well, it's because if it's under, actually this should say the area under a curve is negative when it is under the x-axis, because when we talk about the area, we talk about it from the curve to the x-axis. So when I fall under the curve right here, the reason why we would say that the integral is negative is because the f of x is negative. So the heights are actually falling below the x-axis. So although we would consider the height of those triangles or rectangles, we'd consider them positive. When they're put in as f of x, they're actually negative values of the function. So really what this integral gives us is what I would like to call the signed area between the curve and the x-axis. So using that, I'd like you to go to, in your notes, yours is right below there, the problem that looks like this, that I took right out of your book, number 47. So it's piecing together different parts right here. Notice we're going right here, so I have a triangular portion of the graph right here. Right here I have a semicircle, and right here another triangle, and you're going to be asked to find different integrals, or definite integrals is what we call them when we've got the limits of integration on there. And so really what this is saying is find the signed area from 0 to 2 of f of x. So really from 0 to 2 is this way. And so I'd be asked to find the area of this quarter circle, but it's actually a signed area because it's falling below the x-axis. So the integral for this region is going to be negative, these are negative, and this is positive. So although we say it gives us area, the integration actually gives us what we call a signed area. So what I would say is because that's below the x-axis, the integral is negative, and it'd be 1/4 pi times the radius squared. And I'm not going to finish that off. Likewise, when I go from 2 to 6, and I find the integral, which basically means the signed area, that means I am integrating from 2 to 6 this way, and it is above the x-axis. So both my dx, my delta x, and my f of x are positive, so we would consider this positive integral up here, and it's just the area of the triangle. So I do 1/2 of its base, which is 4, times its height, which is 2, and so that would be a positive 4. Now, had that fallen below the x-axis, we would say that's negative 4. So now you're going to kind of have to watch whether your integral is positive or negative, because to say that integrating gives us the area between the curve and the x-axis is almost false, because it gives us what we call the signed area. So you've got to watch out for whether you're above or below the x-axis. So for part C, we'd be integrating from negative 4 all the way to 2, and that's all below the x-axis. So what that tells me is it would be negative. And then I would just find the area of the triangle, 1/2 base times height, plus area of the semicircle, which would be pi r squared divided by 2. They are both negative, so my answer would be adding those up and then saying it's the opposite. I'm not going to complete that. I'd like to go discuss letter E. Now when it says to do the absolute value of f of x, now that's a little different because that means everywhere it went negative, you should make it positive. So the absolute value of f of x will take all those places where f fell below the x-axis or went negative, and I'll make it positive. So when I do that and I go all the way from -4 to 6, basically what that means, I'm going to label these 1, 2, and 3, is I just do 1 plus 2 plus 3 and use all their positive areas. All right? And I'm going to move right along here. That's enough on that. So what I'd like you to do now is go to the page that looks like this, 4.3. And it says, so the area under a curve can be found by integrating. And we've written that a couple times. But again, that gives us the signed area. And it's actually under the curve and between the curve and the x-axis, to be more specific. This is actually called a definite integral. Whereas what we dealt with in 4.1 with anti-differentiation is called an indefinite integral. The difference visually is that the definite integral has what we call limits of integration. The difference specifically is that the definite integral gives us the signed value of the area between the curve and the x-axis, whereas the indefinite integral is asking you to find an antiderivative. And although they seem very separate right now, I told you they will get married in a little bit. And before we can use that definite integral to give us the exact area and tie it into the anti-differentiation process in 4.1, and it's so huge, it's actually called the fundamental theorem of calculus. We're going to call it the FTC. It's in like the top 5 of mathematical equations of all time. You'll see why when we get there, but before we can tie those together with the final knot, there's some properties that go with the definite integrals that I would like you to get used to using. And the first one says that when you integrate from A to B, it's the same as opposite of going from B to A, which should make pretty much sense, because when I reverse and go from B to A, what I'm doing is heading this way. So my dx becomes negative right here. So if I want it to be equal to that way, I'd have to do negative, negative. But basically what that is saying is that if you integrate from 1 to 3 of f of x, you can tell me that that's the same as the opposite of from 3 to 1, f of x dx. Because this would actually be negative in this calculation, and the two negatives would make the positive and make them equal. All right, so part 2 says, well, if you have the same limits, what is it? Well, kind of think of that with common sense. If I'm integrating from 5 to 5, I actually have no x. It's actually 0. So it's just 0. The integral from 3 to 3 of any function is just 0. We also have the scalar multiple rule that says you can bring any constant multiple out front of your integral. We have the sum and difference rule, just as we've had for our derivatives and for our indefinite integrals. And it says that if we have a sum or a difference, we can perform them separately and then simply add or subtract them. We've had that one before. The next one is one that's used quite a bit, and I'll explain it with a picture once I write it out. It says that if you're going to integrate from A to B, it's legal to go from A to C, and then from C to B, and you would have the equivalent of just going from A to B. What does that mean on a picture? It basically just says this. If A is here, and B is here, and if I put a C right here, it's saying I can integrate from A to C, which would give me that area, and then I could go from C to B, which will give me this area, and what I end up with is the area all the way across, or the area from A to B. The last one, actually, I'm going to leave off until we get to another section. So there's a benefit to writing them all out, but just in case you missed some of the explanation and taking the notes, I've also re-put those on the top page. So this top blue box is basically everything I just said with it written out. So let's go take an example from the book. We'll look at example number, I wish I could see my timer here. I don't know how much time I have left. But my example number 6, it has some constant multiples. It's got a sum, it's got a difference. And what I'm going to use is those properties above to break that apart and then use these specific recalculated values. So what I'm being asked to do is find the area between the curve and the x-axis of this parabola. It's one that opens down, you could graph it, etc. You could even use the Math 9, which I've already taught you how to do, but that's not what this one wants. They want you to use the properties above that say that the constant can come out front, so I'd have the opposite of from 1 to 3 of x squared dx plus, again, that's a constant multiple, it can come out front. So I'd have the integral from 1 to 3 of x dx minus, again, this is a constant, it would just come out front. I'd basically leave a 1 in there if you want to picture it like that. And then they have given me all those values up above here. It says the area under the curve, or the definite integral, is 26/3. I had a negative in front of that, plus the integral of x dx, the value of that is 4, so I'd have 4 times 4 when I replace this. Likewise, the just 1 dx, or dx is 2, so I'd have minus 3 times 2, and you would go get me a single answer for that. So moving right along here. Number 42 from your book, and again I'm taking an example similar to your homework. So what we're going to do is use those properties to tweak the integrals given. Now they have told me what's happening from 0 to 3, the area under my function in the x-axis is 4, and they're telling me this one's negative 1. What they're basically telling me for this one is that it fell below the x-axis. So I've got two pieces, from 0 to 3 and 3 to 6. And part A just says go from 0 to 6. Well, that would just be from 0 to 3 plus from 0 to 6, which is 3. This one's obvious because I'm just going from 3 to 3. That means dx is 0. I have no delta x. I am just basically, I have one thing. I can't have any area there, so that would be 0. Now from 6 to 3, they didn't give me 6 to 3, but they gave me 3 to 6. And we have a property that says if you're going to change the limits, you have to take the opposite. If you look back, I believe it was property number 1 actually. So it would be that, which would be positive 1. All right, so next, let's see what we've got here. This one uses two properties. We're going to take the negative 5 out front and then go from 3 to 6. And then go see if they gave you from 3 to 6, and they did. So that's just going to be negative 5 times negative 1, which is 5. So you'll be using some of that. Number 52 I took from your book. I'm not going to do all of them, but I will do a couple. This is finding the missing A and B to make this a true statement. Well, if I go from negative 2 to 1, and then from 1 to 5, I might as well have just gone from negative 2 to 5. That's all this one is saying. Let's go down and take a look at part D. It says to find the missing limit so that the cosine of dx, when you integrate it, of x, is equal to 0. What that's saying is I want to set up my limit so that when I find the area between cosine curve and the x-axis, it balances out to be 0. For that to happen, it means I must have an equal amount below the curve as above the curve. Because when it falls when it falls below the x-axis, our definite integral is negative. So let's see, let's put a sample of the cosine wave up here. The cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1, so this is at pi. Cosine 3 pi over 2 is back to 0. And the cosine of 2 pi is back to 1. So here's a cycle of my cosine wave, and I could continue it back like this also. And there's an infinite amount of right answers, but really when this is saying it balances out to be 0, it means I want to have an equal amount above the x-axis as below. So I think probably what I want to do is maybe just go from here to here. This would have a positive area, and this would have the exact same negative area. So I could have A be negative pi over 2, and I could integrate all the way over to this one, which was my 3 pi over 2. And if I did that, I will get a signed area, which means I will get a positive for this and a negative same amount for this, and it'll balance out to be 0. just so you know how that works. On the last one that I'm going to do with you today here, it says that you are, this is a really good kind of AP type of question to be done without a calculator, because it means you really understand what you're doing when you're being asked to find a definite integral. I want to know approximately, and these are really far apart, by the way, so what the definite integral would be, which really means what's the area of the curve beneath this function, and